Identifying and verifying an AP. Hello everyone. Today, we are moving on to a very practical skill in our study of sequences, identifying and verifying an arithmetic progression, or an AP for short. Now, in our previous lessons, we already established the definition of an arithmetic progression. We learned that it is a sequence where the difference between any two consecutive terms remains constant throughout. But here is the catch. In a real exam or a complex math problem, you won't always be told that a sequence is an AP. Instead, you will often be handed a random list of numbers and tasked with determining for yourself whether that list actually follows that constant pattern. This specific process of checking the numbers to prove or disprove the pattern is what we call verifying an AP. Over the next few slides, I will show you the exact mathematical principle and the step-by-step method you can use to verify any sequence with confidence. The fundamental principle of verification. Now that we've introduced the concept of identifying an AP, let's look at the fundamental principle we use to actually verify one. When we talk about verifying, we aren't just guessing, we are looking for proof. To verify if a sequence is an AP, we must ensure that the common difference is truly common to all terms. It's not enough for just the following two numbers to have a specific gap. That gap must persist throughout the entire list. What does this mean in practice? It means the difference between the second term and the first term must be exactly the same as the difference between the third term and the second term, and so on through every single term in the sequence. If you want to see how we express this mathematically, look at this notation. A sequence, which we can call a sub-1, a sub-2, a sub-3, all the way to a sub-n, is an AP if and only if. A sub-2 minus a sub-1 equals a sub-3 minus a sub-2 equals a sub-4 minus a sub-3, and so on, all the way up to a sub-n minus a sub-n minus 1. In short, if that subtraction result stays identical every single time you move to the next pair, you have successfully verified an AP. In the next slide, I will show you a systematic, step-by-step method to perform this calculation without making any errors. Step-by-step process to verify an AP. Now that we understand the fundamental principle, that the difference must be truly common to all terms, let's break this down into a clear, systematic process. If you follow these 5 steps, you will never be caught off guard when asked to verify a sequence. Step 1. First, we need to identify the terms. Don't just look at the list of numbers as a random group, label them clearly. We call the first term a sub-1, the second term a sub-2, and so on, all the way up to the last term, which we call a sub-n. This keeps our work organized. Step 2. Next, we calculate the first difference. To do this, take the second term and subtract the first term from it. We'll denote this first result as d sub-1. Step 3. Now we move to the second difference. We do the same thing with the next pair, subtract the second term from the third term. We'll call this result d sub-2. Step 4. This is a crucial part of the process. Compare the differences. Look at your result from step 2 and your result from step 3. If d sub-1 does not equal d sub-2, then you have found your answer immediately. The sequence is not an arithmetic progression. You don't need to waste any more time, you can stop right here. However, if d sub-1 does equal d sub-me, then you have a potential AP, and you must proceed to the next step. Step 5. Finally, you must verify the remaining terms. You cannot assume the pattern continues just because the first 2 pairs matched. You must continue subtracting each term from the one that follows it, for example, calculating a sub-4 minus a sub-3, and then a sub-5 minus a sub-4. If this difference remains constant for every single pair of consecutive terms in the entire list, then, and only then, can you officially verify the sequence as an arithmetic progression. We will apply this exact step-by-step method in the upcoming examples to see it in action. Illustrative examples. Now that we have understood the theory and the step-by-step process for verification, let's put it into practice with a real-world scenario. Imagine a student who has decided to start a savings plan using a piggy bank. In the first week, they deposit $50. In the second week, they deposit $75, followed by $100 in the third week, and $125 in the fourth week. Looking at these numbers, our goal is to determine, does this sequence of weekly savings form an arithmetic progression? To find the answer, let's follow the systematic steps we just discussed. First, we need to identify our terms clearly. We can label our sequence as a sub 1 equals 50, a sub 2 equals 75, a sub 3 equals 100, and a sub 4 equals 125. Next, we calculate the first difference by subtracting the first term from the second term. That is, a sub 2 minus a sub 1, which is 75 minus 50, giving us a result of 25. Now we move to the second difference. We subtract the second term from the third term, a sub 3 minus a sub 2, which is 100 minus 75, which also equals 25. To be thorough, we must continue the process for the third difference. We subtract the third term from the fourth term, a sub 4 minus a sub 3, which is 125 minus 100, resulting in 25 once again. Finally, we look at our results to reach a conclusion. Because the difference remains constant at 25 for all consecutive terms, we can officially confirm that the sequence 50, 75, 100, and 125 is indeed an arithmetic progression. But remember, just because this one works doesn't mean every sequence does. Let's look at our next example to see what happens when the pattern breaks. Illustrative examples continued. Now that we have seen how a consistent difference confirms an arithmetic progression in our first example, let's look at something different. In example 2, we are going to verify a non-AP sequence. Here is the sequence we are investigating: 2, 4, 8, 16, and 32. Our goal is to determine if this list follows the rules of an AP that we discussed in the previous slides. Let's walk through the solution step by step using the systematic process I just showed you. First, step 1, identify the terms. We will label our terms clearly. The first term, a sub 1, is 2, the second term, a sub 2, is 4, the third term, a sub 3, is 8, the fourth term, a sub 4, is 16, and the fifth term, a sub 5, is 32. Next, step 2, calculate the first difference. We subtract the first term from the second term. That is, a sub 2 minus a sub 1, which gives us 4 minus 2, resulting in a difference of 2. Now, step 3, calculate the second difference. We move to the next pair and subtract the second term from the third term. That is, a sub 3 minus a sub 2, which is 8 minus 4, giving us a difference of 4. In step 4, we compare the differences. This is the most critical part of the verification. We observe that our first difference, which was 2, is not equal to our second difference, which was 4. Finally, step 5, conclusion. Because we found that the difference is not constant, we can stop right here. We have proven that the sequence 2, 4, 8, 16, and 32 is not an arithmetic progression. As we will see in the next slide, it is very easy to mistake this type of sequence for an AP. So pay close attention to the difference between adding a constant and multiplying by a constant. Common mistakes to avoid. Now that we have seen how to correctly verify an AP through our examples, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make small errors that lead to the wrong conclusion. First, let's look at the incorrect order of subtraction. When we are calculating the common difference, I have seen many beginners accidentally subtract the larger number from the smaller one, or they switch the order inconsistently. To avoid this, you must always follow one strict rule: always subtract the preceding term from the succeeding term. In other words, take the later term and subtract the earlier term. For instance, the correct way to write this is a sub 2 minus a sub 1. An incorrect approach would be a sub 1 minus a sub 2. If you flip this, you might end up with a negative difference when it should be positive, which will confuse your entire calculation. Second, watch out for stopping too early. It is very tempting to look at the first two pairs of numbers, see that they have the same difference, and immediately declare, yes, this is an AP. However, as we saw in our previous examples, a sequence can look like an AP at the start, but change its pattern later on. To formally verify a sequence, you cannot be lazy. You must check every single pair of consecutive terms provided in the list to ensure the difference remains constant until the very end. Finally, there is the confusion with geometric progressions. This is a very important distinction. Sometimes, you might encounter a sequence that grows very quickly, like the one we looked at in example 2, where each number is multiplied by 2. Students often mistake this type of growth for an AP, but remember, an arithmetic progression is strictly about addition or subtraction. If you see a fixed multiplier instead of a fixed difference, you are dealing with a different type of sequence entirely. Keep these 3 points in mind, and you will avoid the most common traps in this topic. Now, let's wrap up with our key takeaways. Key takeaways. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid foundation for your upcoming practice problems. First, let's look at the formal verification rule. Mathematically speaking, we say a sequence is an arithmetic progression if and only if a sub k plus 1 minus a sub k equals d. For all values of k in simpler terms, this is just the formal way of saying that no matter which pair of consecutive terms you pick, the result of subtracting the earlier term from the later term must always equal that same constant difference, which we call d. Second, remember that consistency is key. It isn't enough to just find 1 or 2 matching differences. For a sequence to be officially verified, that difference must be identical across the entire sequence, from the very first term to the very last. Third, keep an eye out for the stop condition. This is a great time-saving tip for your exams. As soon as you find even a single pair of consecutive terms where the difference is different from the previous pair, you can stop calculating immediately. The sequence is immediately disqualified from being an AP, so there is no need to waste time checking the remaining numbers. Finally, always remember that order matters. As we discussed in our common mistakes slide, you must always subtract the term at position n from the term at position n plus 1. Always take the succeeding term and subtract the preceding term. If you flip them, you might get the wrong sign, which could lead to errors in your calculations. Keep these principles in mind, and you'll be able to identify and verify any arithmetic progression with confidence. Great job today!